All right, so this is 9.5, the dot product. Our first learning objective is to find the dot product of two vectors. This is vectors version of multiplication. So you can't really multiply two vectors together because there's things going on in a vector, a direction and a magnitude. So you can't just straight up multiply those two things, two vectors together. But there is a process called the dot product. And if you have a vector v and a vector w, where each of them are split up into their I and j components, the dot product v dot w is defined as the coefficient of the I component multiplied plus the coefficient of the j component multiplied. A1 times A2 plus B1 times B2. So as you can see, the dot product results in a number. So it won't pop you out another vector. When you take the dot product of two vectors, it gives you out a number, an important difference, because if you try to plug in a vector as an answer, then it will be wrong. Okay, so let's do some examples. If you have v is equal to negative 3i plus 4j, and vector w is 2i minus 5j. Let's go ahead and do the dot product of v and w. So we're going to take negative 3 times 2 to get negative 6, and we're going to take 4 times negative 5 to get negative 20. So the dot product of v and w is negative 26. Let's see if we reverse that order. Let's see if we'll get the same result. So if we do w dot v, we get 2 times negative 3 plus negative 5 times 4. That still is negative 6 minus 20, and we still get negative 26. Sometimes we will multiply or find the dot product of a vector by itself. So when we do that, we get negative 3 times negative 3 plus 4 times 4, which is 9 plus 16, and that's 25. W times w, or w dot w, is 2 times 2 minus 5 times negative 5, which is 4 plus 25, and that gives you 29. We're going to go ahead and do a little refresher on magnitude. So the magnitude of v, that's when we take the square roots of each component squared. So vector v is square root of negative 3 squared plus 4 squared. That's 9 plus 16. That's 25, and the square root of 25 is 5. The magnitude of w, we're going to do the same thing. We're going to take 2 squared plus negative 5 squared and square root it. And we get we get square root of 29. Check this out. The dot product in relationship to the magnitude. Is there a relationship between the dot product of a vector and itself and its magnitude? Can you find the relationship? All right, so what we saw is that if u, v, and w are vectors, the commutative property says it doesn't matter if I multiply u times v, or find the dot product of u and v. It's the same as the dot product of v and u. Distributive property says if I find the dot product between u and the resulting vector of v plus w, it's the same as finding the dot product of uv and adding it to the dot product of uw. The dot product of a vector in itself is the same as the magnitude squared. And then the dot product between 0 and a vector is 0. Okay, if we have two vectors and we want the angle theta in between those two vectors, we are going to use our old friend, the law of cosines. The u minus v vector squared is equal to, the magnitude of the u minus v vector squared is equal to the magnitude of u squared plus the magnitude of v squared minus 2 times u times v, magnitude of each, times the cosine of theta. So we're going to plug in those magnitudes, then solve for cosine theta, then inverse cosine to find theta. And when we do that, we find that the cosine of theta is the dot product between u and v divided by the magnitude of u times the magnitude of v. And that'll give us an angle in between 0 and pi. All right, so if we want to find the angle theta between u and v, we're going to use cosine theta. So we're going to use this formula down here. We go ahead and get a picture of that. So if you look, theta is less than 180 degrees. That's why it's between 0 and pi. And we're going to go ahead and use this. So we got to find the dot product between u and v. So that's 4 times 2 plus negative 3 times 5. That's 8 minus 15, which is negative 7. So this part up here becomes negative 7. I need to find the magnitude of u, which is 4 squared plus negative 3 squared. That's 16. This is wrong. Okay. Sorry, this is correct. 16 plus 9 is 25, and the square root of 25 is 5. And then the magnitude of v we found in the previous problem. 2 squared plus 5 squared, square root is root 29. And we're going to put all those together into this formula. Cosine theta is equal to negative 7 divided by 5 root 29, which is approximately equal to negative 0.26. We inverse cosine and find that theta is 105 degrees. Okay, figuring out if two vectors are parallel. If two vectors, v and w, are parallel, if there is a non-zero scalar, alpha, so that v equals alpha times w. In this case, the angle theta between v and w is 0 or pi. So if they're parallel, then the angle is going to be 0 or pi. So if we look at two vectors, vector v equals 3i minus j and vector w equals 6i minus 2j, you can say that they're parallel since vector v is 1/2 vector w. But we can also say that they're parallel since when we look at our formula for cosine theta equals the dot product of v and w divided by the magnitude of v times the magnitude of w. The dot product is 3 times 6 is 18. Negative 1 times negative 2 is 2. So our top is 20. The magnitude of vector v is 3 squared plus 1 squared, which is square root of 10. And the magnitude of w is 6 squared is 36 plus 2 squared is 4. That's the square root, that's 40. 10 times 40 is 400. Square root of 400 is 20. 20 divided by 20 is 1. Theta, that gives you a cosine of 1, is 0. So the angle between V and W is 0. So both of those can be used to say that the vectors are parallel. Now we're going to figure out whether two vectors are orthogonal. If the angle theta between two vectors V and W is pi over 2, then the vectors V and W are called orthogonal. So V is orthogonal to W if the angle between them is 90 degrees. We can tell if two vectors are orthogonal if when we take the dot product, we get out 0. We take the dot product of two vectors and get out 0, then we can say, yes, they're definitely orthogonal. All right, so let's see how this looks. If I have V equal 2I minus j and W equal 3I plus 6j, I find the dot product. So I go 2 times 3 is 6. Negative 1 times 6 is negative 6. 6 minus 6 is 0, so these are orthogonal. All right. Decompose a vector into two orthogonal vectors. Here's an example. So if we have this is a vector f, we can write vector f as a product of two orthogonal vectors. So we say f is equal to f1 plus f2, and f1 and f2 are orthogonal. This is useful when we're doing force or work problems, so that's why it may seem silly to take a vector and decompose it into two orthogonal, but that's the way we roll to solve some problems. So like vector v is split up into v1 plus v2. This vector v is split up into v1 and v2. All right, so if v and w are two non-zero vectors, the vector projection of v onto w is v1 equals the dot product of v and w divided by the magnitude of w squared times w. The decomposition of v1 into v1 and v2, so it's where we take our vector and split it into two components, where v1 is parallel to w and v2 is perpendicular to w, is the dot product of v and w. Oh, so v1 is equal to this this quantity, so this gives you a value, and then times the vector w. The dot product of v and w divided by the magnitude of w squared times the vector w. v2 is equal to v minus v1. And we'll show you why this is all meaningful in just a moment. Okay, find the vector projection of v equals I plus 3j onto w equals I plus j. Decompose v into two vectors, v1 and v2, where v1 is parallel to w and v2 is orthogonal to w. So the picture looks like this. W equals I plus j, so that's over 1 up 1. And v equals I plus 3j, that's over 1 up 3. And we are going to find V1, which is parallel to W, and V2, which is orthogonal to W. So V1 is this guy, and V2 is going to be this guy. So the dot product between V and W is 1 times 1, which is 1, plus 3 times 1, which is 3, divided by the magnitude of W. So that's 1 squared plus 1 squared, which is 2 squared. The magnitude is the square root of that. And then we're going to square the square root of 2. So we get 4 over 2, which is 2. So V1 is equal to 2 times W, or 2 times I plus J. That's why they get this. V2 is our original V vector minus V1. So that's I plus 3J minus 2 times I plus J. So that is 1I minus 2I's to get negative I. And that's 3J's minus 2J's to get 1J. So it's I plus J. Sorry, negative I plus J. All right, let's get down to the important stuff. Finding the force required to hold a wagon on a hill. Your book has a bunch of really good examples of the force vectors, and I'd recommend, because there's too many to make our time efficient, to look them over all together. I definitely recommend you looking over all those example problems that are in this section of the book. A wagon with 2 small children as occupants that weighs 100 pounds, this guy right here, is on a hill with a grade of 20%. What is the magnitude of the force that is required to keep the wagon from rolling down the hill? So the first thing we look at is force of the weight. So your weight, thank you gravity, shoots you straight down in the negative J direction. So whatever you weigh, that's the scalar that multiplies the J in the J direction. So we know FW is equal to negative 100J. Negative 100 because the force is acting downward. That's how gravity works on our planet. We know our W vector is cosine 20 degrees because we have the I is the horizontal component and the J is the vertical component. So we know that the force acting in this W direction is cosine 20 degrees I plus sine of 20 degrees J. We know that this vector V, which has to counteract W, they have to be parallel to each other, and it has to be, the force has to be in the opposite direction so that poor little wagon doesn't roll downhill and your children fall and hurt themselves. Has to be in the opposite direction as this V. So we're going to find this V vector. It's our force vector, dot product with W, divided by the magnitude of W squared times the W vector. All right, so we go, the magnitude of the force, it's negative 100J times the sine of 20, because 0 times cosine of 20 is 0. So that leaves this dot product being negative 100 sine of 20, divided by cosine 20 squared plus sine 20 squared square root, and then times the W vector. Cosine 20I plus sine 20J. You chug this into your calculator and you get negative 34.2 cosine 20I plus sine 20J. the magnitude of V is 34.2 pounds. So the magnitude of the force required to keep the wagon from rolling down the hill is 34.2 pounds. All right. We're going to do this. All right, so now we're going to do an example of a work problem. In elementary physics, the work W done by a constant force F in moving an object from point A to point B is defined as the magnitude of force times the distance. So it's the magnitude of our force vector times the magnitude of our distance vector. For example, I got this guy pushing the cabinet. He is pushing at some distance A to B, so he's got a direction and a magnitude. He is, if you look, his force is actually, if you follow the direction, is going in this direction here. So he's applying a force in this direction. So the amount of work he's doing is that force vector times the AB vector. I mean dot product. Dot product. It's not times. All right, so let's see what this means in a real problem. We got our girl. She made it out of the wagon. Good job, little buddy. Now she's pulling it with a force of 50 pounds. She's a really strong little girl. How much work is done in moving the wagon 100 feet if the handle makes an angle of 30 degrees with the ground? All right. So if we break down this problem into a nice little XY graph, we have our starting point is 0, 0. She's going to move it 100 feet. We look at this angle is 30 degrees, they tell us. And our force is, the magnitude of our force is 50. So our I component to our force vector is 50 cosine 30 degrees I. The Y component to our force vector, our vertical force, is 50 sine 30 degrees J. So if we go ahead and find the exact values for cosine 30, which is root 3 over 2, and sine of 30, which is 1/2, and then we simplify this down into, this is both divided by 2, so we can factor out a 1/2. 50 times 1/2 is 25, and I get 25 times root 3I plus J. Work is equal to our force vector dot product with AB. So we take our AB vector, which is 100I, and find the dot product between 25 times root 3I plus J. And we get 2,500 root 3 foot-pounds. And that's it.